I also would like to welcome you for this first session on sensor web technologies. What I will do is give you a quick fundamental introduction into the core standards of the sensor web framework, especially those of the OGC. So we will have a look at an overview of the whole architecture, and afterwards we will go into three core standards. On the one hand, observations and measurements, which gives us some indication and guidance how to model different types of observation data, how to represent that as XML or other formats. Then we will have a look at the OGC SOS specification, and finally we will also have a closer look at the OGC SensorThings API, which is another efficient means for delivering observation data. So these are the three standards which we will introduce, and especially for the last of these standards, the SensorThings API, we will also do some practical interactions with an instance to illustrate you a bit more how to use such a type of service. Okay, so with that, I will go into the core of this tutorial. So you should be able to see my screen. And first, let's talk a bit about the motivation. So why are we talking about standards? Why do we want to share observation? And there are more and more sensors being deployed. So you see that in many different domains, in environmental sciences, in hydrology, traffic management. So there are more and more sensors being deployed, and also more types of sensor data becoming available. It's about lots of different types of data, lots of different sensors which are becoming available. So that could be air quality sensors, weather stations, etc. And with that, we would like to provide means and approaches that help us to provide people with access to these data, provide scientists with a common way to download the data and do their analysis work with this type of data. So what's important to consider here is that there are different structures. So depending on the sensor that you're using, the data may have different structure, different formats. So the interfaces for downloading the data can be very heterogeneous. So for example, there can be Internet of Things protocols which are used, streaming-based protocols. There could be old-fashioned FTP servers where some CSV data is stored, etc. So, and the idea is now to provide some kind of harmonization layer that facilitates the integration of all these different types of data. And that means we would like to have some interoperability between different types of sensor systems, also perhaps between different domains. So for example, you may want to combine hydrological measurements with some weather data. And for that also, it's really helpful if you have a common way to share this data. To illustrate this a bit more, why standards are something which help us in practice, let's consider you have three different observation networks. So these are shown here below. And each of these networks is providing us different types of observation data, and each of these observatories is also using different protocols, different data formats. And then you have different data consumers. So one may be some GIS, where people want to do some spatial analysis. There may be web clients for presenting the data on the web, or other desktop systems where you would like to do some complex statistical analysis, like, for example, R. And with that, there's a problem now how to get these data into these different target systems. If we add further networks which we would like to consume, and if we add further clients, you will see that the integration efforts for customizing each of these systems to consume data from each of the data providers would explode. And that's the idea where standards come into play, and where we would like to have some kind of abstraction layer that helps us to facilitate this integration process. One opportunity is the OGC SOS, another one would be the SensorThings API, which give us a protocol for asking for the data, and then also have common encodings, common language for sharing the data and providing access to it. So that's the basic idea which we are talking about. And to enable this, we will now have a look at the OGC, the Open Geospatial Consortium, which has been quite active in the past to specify different types of standards for sharing and exchanging geo-related information. So perhaps most of you will be familiar with the established OGC standards such as Web Map Service, Web Feature Service. In that context, perhaps also the emerging OGC API, which also now has a module for feature access, processing, where you will hear also about information about during this conference. Some of you may have heard about common data models and encodings from the OGC, such as GML, KML. And within this whole framework of OGC standards, which are aiming to facilitate the sharing of information via the web, there is also a dedicated subset dealing with the integration of observation data, and that's called Sensor Web Enablement. And around this suite of standards, that's where we will center our tutorial to this morning. So let's have a quick overview what's in there in the world of Sensor Web Enablement. In the traditional way, we have two types of standards in there. We have data models and encodings, and on the other hand, interfaces that allow us to access or do some function calls on servers. So regarding the data models and encodings, there are two very important ones. The O&M, Observations and Measurement Standard. That's also an ISO standard, which allows us to describe the core properties of observation data. So describe what are the core fields of an observation, which information does need to be provided. There we will have a look on the subsequent slides a bit how such an observation data element would be structured and derived from O&M some specializations, WATERML, TIMESERIESML. So these are specific types of this standard for specific types of data. Complementary to observations and measurements as the data format, there's also SensorML for encoding metadata about the processes through which data was acquired. So like information about the sensor hardware, but also information, for example, about processes that were applied to the data, like calibration, some quality checks, quality control, harmonization of data, etc. So everything which we have done to our data, that can be described with this SensorML standard. So that's our two data models, data standards, O&M for the data itself, SensorML for the metadata. And on the other hand, we have our interface standards. And here I would especially look at the OGC SOS, Sense Observation Service, which is the interface which we can use for querying the data. So we can tell the server, I would like to get data for a specific station for a certain property, and then we get this relevant subset of data back. In between, I have here the OGC SensorThings API. That's the most recent standard in this suite of standards. And this is a standard which I could not put into one of these boxes because it follows a different paradigm. So here we have the typical and the classic standards here, O&M, SOS. This is a classic remote procedure call on a server. With the SensorThings API, we go to a REST approach. So it defines, on the one hand, how to use HTTP operations to do something with sensor-related resources. And it also defines how these sensor resources, that could be a data stream coming from a sensor, the observations in the sensor, the locations, how that shall be encoded in JSON. It's somehow related to O&M because it uses core features of that data model. However, as it defines both a protocol and an encoding, it's somewhere here in between and not in one of these big boxes like encodings and interfaces. I will illustrate that later a bit more to give you some more insight how to use and interact with that server. Okay, so that was the overview. Lots of acronyms. So sometimes people are a bit shocked when they first get into touch with this whole framework of different standards and acronyms. Don't remember all of this. Just take with you sensor web standards of the OGC give you opportunities for encoding measurement data, for encoding metadata, and for providing you protocol specifications, how to access this data from a server, for example. And now we will go into the foundations. And the first thing we will look here at is the observations and measurements standard. So this is quite fundamental because it defines us or gives us some very important guidance how we should model our observation data sets, how to organize the data. And this is available as an ISO standard. It's published by the International Standardization Organization. At the same time, it's an OGC standard, so there's a close cooperation between these two standardization bodies. However, with ISO, we are getting this as a de jure standard, which is, for example, also referred then later on by more fundamental frameworks such as INSPIRE. The ISO standard provides us with an abstract data model, which I will introduce on the next slides. At the same time, there's an additional OGC standard, which also provides information how to encode this as XML. And besides this XML standard, there are also now best practices and recommendations how this abstract ISO data model can be encoded in practice, for example, in other formats such as JSON. So ISO gives us the conceptual model, OGC tells us how to put that as XML or JSON, for example. And now let's have a look at one observation data element. For describing or for giving us all the information that we need for interpreting a measurement values, we need some more context data. So let's have a look at this. So we have a sensor mounted at a certain location, measuring something at a certain date, etc. And for this, we have different properties defined by the O&M standard. So the first one is that we all this consider as an observation, that we consider this as an observation as a whole. And then within our observation, we have different types of information. So a specific sensor has measured something. That's the procedure, how the measurement was obtained. So for example, it could be just a reference to a sensor. It could be an identifier of a specific sensor system. It could also be a reference to an algorithm which we use for calculating an hourly mean for rainfall. So that's our procedure, the way how the data was generated. Then we need some information, where was this measurement taken? That's our so-called sampling feature. So here you see coordinates which help us to georeference the measurement that we have taken. In the next step, we also need to know what was measured. So in this case, we have measured the water temperature. If we just have a value of 6 degrees Celsius, without any further information, that could be air temperature, ground temperature, water temperature. And with this information, we get the information we are here dealing with water temperature. Then we can put our measurement in a larger context. So above you have seen the coordinates. However, you may want to put that in a larger context. So like the information, the measurement was taken at the River Elbe. So some further information that we have here. Then we have our core result. So that is the value that was measured together with the unit of measurement if applicable. So in this case, we have numeric result. However, in other cases, we could also have more complex results that could be, on the one hand, images taken, could be simple Boolean values. It could also be references to more complex data sets. So, for example, we have also scenarios where a sensor generates a complex netcdf file, and at this part, we could reference there to this other external files. So the result is quite flexible, but in the basic case, we assume here a numeric value with a unit of measurement. Next thing is to which point in time this measurement applies. So here we get the information. Okay, the temperature at 17:45 on the 20th of January this year was 6 degrees Celsius. So the timestamp referring to the information to the point in time when this value applies. And finally, You may have some more complex process that there will be some validation before the data is published. And in this case, we have the additional timestamp, so-called result time. And this timestamp basically tells us when the data was published. Here for the result time, here we have the example of a validation workflow, which is completed before publication. In other cases, some of you may deal with samplings taken at a lake, and then the sample is taken to a laboratory where it is analyzed. And after 2 days of analysis, the value is published. Then we would have the phenomenon time at the point in time when the sample was taken, and the result time would indicate when the data was published. So these are the core properties defined by the O&M observations and measurements standard. And this gives us some guidance later on what we need to consider when working with observation data. Here you see again some explanations, so that's perhaps more intended for later reference if you would like to look that up a bit more. We will make these slides accessible to you after the workshop and conference, but this is something which you can use then for looking up what I told you just before. So the observation as an act of observing something, the phenomenon time, the date when a value applies, result time when some data was published, valid time, that is something which I did not mention. Valid time can, for example, be useful if you are dealing with forecast data. An example which we have been dealing with in the past is prediction of water discharge in rivers. And the predicted water discharge depends on some weather models which are running in the background. And every time a new model run has been completed, so a new version of our prediction model run has been completed, then the prediction is replaced. And this valid time basically indicates us how long a value will be valid until the next model run, for example, has been completed. Further, we have the observation process. I mentioned that that's the way how the observation was generated. As I mentioned, that could be an instrument, a sensor, can be a human observer if you look at citizen science projects, can be some process or algorithm which has been applied to do some calculation of data based on raw input data, or finally could also be some kind of simulation. And here we usually have a reference to a SensorML document, sensor model language, which provides us then the detailed metadata about this process which has generated the data. The feature of interest, I mentioned that's our geospatial reference which we have. The observed property is the reference to the parameter which we are observing. One important thing here is that there's a trend towards the use of vocabularies to have also not the syntactic interoperability of the SensorWeb standards, but also to have some kind of harmonized content. An example is to use then vocabularies such as this one down here at the bottom of the slide, the NERC vocabulary server, which gives us a long and comprehensive vocabulary of terms such as observed properties, and puts them to some kind of semantic reference. So by referencing such a dictionary entry, a vocabulary entry, we can ensure that we are using a common terminology. So if we use a vocabulary, we can always refer to this term. If we would not do that, the people can use different styles of writing the properties, so like temp, temperature, air temperature, water temperature, 1,000 different ways to write the same thing. And thus having such vocabulary references helps us to achieve also some interoperability regarding the content. One additional thing which also was not included in this basic slide before is the so-called O&M parameter. This is something which we can use for providing additional information about the measurements which we have been doing. some people use that for having simple quality flags in there, which is quite a valid use case. You can also express that if you have complex observation data, such as a trajectory or profile, where you would like to have some additional information. So if you have a profile, you may express the depth in which a measurement has been taken as an additional information which is necessary to interpret the data. So here the procedure is a quite flexible place to express any further information that you need to correctly interpret your data. The result, I mentioned that. And then let's have a look at the encodings. So before, you have seen this UML diagram, which is basically forming the core of the OGC specification, the ISO specification for the conceptual O&M model. And then there are now different ways how to express this in concrete encodings. And for that, we have different standards available, which all go back to the same conceptual model. And I would like to introduce a few of them. So one option is to use so-called plain O&M, plain observations and measurements. That's the core ISO, core OGC standard. Then we have some derived standards such as WATERML, which is especially suited for hydrological measurements, hydrometric measurements, TIMESERIESML for time series data, and also the INSPIRE technical guidelines for the use of O&M, which provides some further information how specific types of data could be or should be encoded in O&M. But we will come to this soon. So first one, which I would like to show you, is plain OGC XML encoding. Not too much in detail here, just to give you an idea. Basically, you will find all the different types of property and element that have been defined by the ISO standard here as dedicated XML elements. So the phenomenon time, the result time, the procedure, the parameters, observed property. So all this has now been transformed into an XML representation. And for real observation data, all these elements then would be filled with the corresponding information. So this is just a rough structure how such a journal XML encoding of O&M looks like. If you like, I can also provide you some further example after this workshop. Next step is WATERML. WATERML is basically a specialization of the more generic ISO observations and measurement standard. It's also based on XML and has been designed by quite a lot of players from the hydrology community, which have been working on this to find a more efficient way that is optimized for the transmission of hydrological data. And I will just give you one short example here. So WATERML also has different types of encodings. And the core feature is that WATERML considers data as time series. So here we have our identifier of a time series. We have then some generic properties about the time series as a whole, as data, about the data. We have the information which is the same for all values that we have, so like the unit of measurement, the aggregation duration, so that is the time how long a value has been measured. So for example, here we have a period of 1 day through which the mean value has been calculated. We have information about the property basically in here, etc. And now the data itself then is encoded in such time value pairs. So in the end, we just have timestamps and a value, and that's a then more compact representation of our time series instead of repeating all the common properties time and time again. Next encoding that I would like to show is TIMESERIESML. TIMESERIESML, perhaps we will not go too much into detail here. Basically, it looks pretty much like SensorML. It has been derived from WATERML 2.0 as a generalization of the principles defined by WATERML for any kind of time series data. It's also based on XML and shall help us to more efficiently share time series data. And then we will go to the Inspire world, which is basically providing some additional information how you can use these OGC standards for providing your observation data in an Inspire-conform manner. For that purpose, there are so-called technical guidelines documents provided by the JRC. So 52 North has also supported JRC in creating these documents. And basically, these documents describe, on the one hand, how to use the interface of the OGC Sense Observation Service as an Inspire download service. And on the other hand, provide guidelines also how to express the observation data shared via such an interface in an Inspire-compliant encoding approach. And this is an image which is quite helpful. Perhaps also, even if you are not dealing directly with Inspire, this schema basically gives you an idea how the different types of data fit into different types of encoding approaches. So, for example, you can see here that you can see, do I have a point-based measurement? So at a fixed location, do I have a moving sensors? Do I have some kind of grid in which I take the observation, or do I take samples? Do I take specimens where the data is, how the data is collected? And then you have the different specializations. So at a single point, you can have a point observation just once, measurements once. You can have a time series if you are measuring multiple times at the same point. You can have a moving sensor. The sensor may be moving vertically. Then you would have, measure a profile, so at different points in depth, or you could measure a trajectory along a certain path. So that's quite nice because it gives you a good overview how different types of sensor data can be organized and which are different characteristics that you need to consider. So here, just as an illustration about the different types of observation data you could deal with, you may have observations at a static point. So, for example, you are measuring the height of a tree that is measured once. The tree would be your feature. You would use some kind of triangulation for measuring the height of the tree. You have one result, and the property is the height. So that's a very simple thing. You do not consider future observations. It's just once at one point, and that's the simplest case. Next step could be some kind of measurement station, like ozone concentration. And here you are usually interested how the value evolves during the time. So here our observation is taken by a certain ozone station, which is located at a certain position or feature. And then our values are, we have multiple values with different timestamps. So we have a time series, so time value pairs as a result. And this is then encoded as such a WATERML time series observation. That's the recommendation of Inspire here. Multi-point observation could be, for example, if you have a weather station network and you would like to measure the temperature at all the stations of your network at the same time. Then, for example, you have a weather station network across Germany and you would like to have the temperature measured today at 12 o'clock. Then you would have one single timestamp. However, multiple values bound to different locations. So that's the so-called multi-point observation, which Inspire defines here. Profile observation could be something that you have a ship taking water temperature measurements or salinity measurements in different depths of the ocean at one point in time. And here you would still have your ship as the procedure or the sample instrument. And the characteristic here would be that you have not time value pair or location value pairs. Instead, here you have a depth value pair or height value pair and other kinds of profiles. Trajectory, that's another option. So you have a ship crossing the ocean and which is measuring the water temperature. And here, again, we have our ship as a procedure with a different measurement device. And our result here would be even a bit more complex. It would consist of pairs of time, location, and value. So that's perhaps the most complex thing foreseen by Inspire here. So just to illustrate, different types of measurement data can be handled in this framework, and the standards provide you here different means to encode this and to manage this type of data. So that was the first big part that I have planned for today. This has introduced O&M, observations and measurements, as a fundamental framework for organizing observation data in a conceptual model, to encode the data in different ways. And from now on, we will have a closer look at the interfaces to see if there are which types of protocols we have for sharing this data, for making this accessible, because until now, we just have an encoding. Okay, then let's continue with the OGC Sensor Web Services. And here we will have a look at two different specifications. One is the OGC Sensor Observation Service, in short SOS. And the second one, which we will introduce a bit more closely, is the OGC SensorThings API. So first thing, the OGC Sensor Observation Service. This is a specification which has been there now for quite a lot of years. I think SOS 1.0 was about 2006, 2007. Then by, I think, 2012, around that, SOS 2.0 was developed and approved by OGC. And it basically offers you a pull-based model for downloading sensor data from a server. Usually it returns O&M encoded data in all the different varieties that you have seen. So plain O&M, TIMESERIESML, WATERML, OGC compliant O&M. And basically the SOS interface tells you which operations are there for downloading the data and how to send such requests to a server to get the corresponding data back. Let's have a look how this works in practice. So the main idea here is now that we have this common interface, XML based usually, which abstracts from all the different types of data management systems that you have below. So that could be a database, some proprietary web service for accessing your data, some real-time systems, simulation models, etc. So basically, it abstracts from all these different ways how the data may be there in reality and gives you just a simple web interface, web service interface to query the data independently how it is stored underneath. So here a short view on the overall model of the SOS. And the first thing here is the so-called SOS core, which we have marked here in the middle. And the SOS core provides us a specification of basically three core operations. The first one is the GetCapabilities operation. This operation describes basically the content of an SOS server instance. So for example, information about which operations are supported, which types of filter are there, which content is offered. So it's basically some kind of handshake if you are developing a client application to check which data is available. Basically, this is specified in a way that it is in line with all other types of OGC services, at least the conventional OGC services. So GetCapabilities is an operation which is mandatory for all conventional OGC services. And here also SOS goes back to this common foundation of specifications. Just a simple example how such a capabilities request would look like. So you have here the URL of your service, and then you append to a URL different types of parameter. You indicate that you are talking to an SOS, that you would like to use the SOS specification for communication. You express the operation name that you would like to call, And then you may also specify the protocol version that you would like to use for some kind of version negotiation. And then you will get the self-description of an SOS server. Next thing is perhaps the central operation of the SOS server, the so-called get observation operation. And this operation can be used for requesting sensor data. So GetCapabilities gives you a self-description of the service. GetObservation allows you to download the data itself. And there are several filters that you can apply. So you can express some kind of spatial filters or filter for specific locations. You can apply temporal filters, such as saying, okay, I would like to get data for January 2020. You can specify which type of observed property you are interested in. So like, I would like to get only temperature measurements. The sensors that have been used for generating the data can be used as a filter. Also the so-called offerings, which are some kind of data set identifier which you could use. Okay, so that's get observation. And to further interpret your observation data set, you can also then use the describe sensor operation to get further metadata. That means with describe sensor, you would ask the server, please give me a description of the process that was used to generate the data. And then you will get back a so-called SensorML, sensor model language file. So another OGC standard, the one for the metadata, if you remember. And there you can get then information about the sensor type, sensor identifier, references to further documentation, calibration information about the sensor. So lots of different additional information items that will help you to understand the content or the process that was applied. That may be useful, especially if you would like to use the data for a scientific purpose, so that you can assess, is the data of sufficient quality for fulfilling the purpose for which I would like to use the data. Here, just a simple example how such a request would look like. Basically, you have again specifying the service and version of the service specification that you're using. The request now would be describe sensor, and then you put in basically an identifier for the sensor or procedure for which you would like to get the description. And optional parameters then include information about the format in which you would like to get the information. In this case, we specify would like to get the description in SensorML and the valid time. If your sensor changes over time, so for example, it is reconfigured, some settings are changed, then you can also ask for the specific sensor description that was valid at a specific point in time, so that you get really the description of the sensor in its configuration when it took a specific measurement. So these are the core operations of SOS. You get capabilities for getting a service description as a handshake, get observation for downloading observation data, and describe sensor for getting the metadata about the sensor data. That's the core. And besides that, there are some further operations which I will not introduce in too much detail right now. So we have the so-called enhanced operations, which gives you, for example, the get feature of interest operation to download geometries of the measurement station, for example, creating a map for all features for which you for which you have data. You have the so-called transactional operations. Transactional means typically I have introduced the SOS to you as a service interface for downloading observation data, but also in the other direction, you can use the SOS for putting observation data into your central data store. So transactional operations for publishing data on an SOS. That could even be a sensor system sending automatically data into that server via the so-called transactional operations. Result handling, you have seen perhaps O&M, observations and measurement, that standard can be quite verbose, so creates a lot of XML volume for rather small data sets. And to handle these use cases where you would like to have a more efficient encoding, you can use the so-called result handling operations, which work with some kind of templating approach. That means you describe the structure of the data once, and then the data is more efficiently returned. in a very compact CSV, so comma separated value style encoding as some kind of near plain text in format. So that's for more efficient data transmission. Additional things are about spatial filtering. Spatial filtering is then interesting if you have moving sensors which are continuously changing their location. Here, just as an example, how that looks like. If you have a quickly moving sensors, you would sometimes like to express the information about the location where a measurement taken very close to the measurement value itself. And this spatial filtering profile of the SOS standard basically defines you how to use this owned M parameter, which I have shortly mentioned before, as a extended meta information about an observation for expressing efficiently the sensor location where a value was measured. So if you are dealing with mobile sensors, that will be something which is interesting. Regarding the bindings of the SOS can use a conventional SOAP binding. So really this full-blown SOAP style of communication, can use key value pair encoding. So that means that you just transmit the request parameters in the URL which you are calling, which is basically what I have shown you in the examples before. And then if you look at the 5 to N SOS, we have some additional supported bindings like plain old XML. That's basically an XML encoding of the request without this SOAP envelope stuff. And on the other hand, some kind of JSON encoding for these requests. So these are, however, not yet specified and are some extensions offered by the 5 to N SOS. Okay, so that's it with the SOS, the sensor observation service. And now we would like to, I would like to get with you into a dive into the OGC SensorThings API specification. And if everything works, we will also see some live interactions with the server, because I think that will clarify a bit more about how to use these standards. Okay, so let's start with the SensorThings API. The SensorThings API is, perhaps the most recent element of the sensor enablement family of standards. It has multiple parts. So today we will talk about part 1 called sensing, which is dealing with accessing measurement data. There are further parts in preparation or even completed. For example, sensor tasking is something. Then there will be an extension about event-based sensor data streams, which is still in discussion. So sensing is the core here, which we will talk about today. It's completely based on REST with a JSON encoding of the different resources. It's quite simplified compared to the SOS. And what's also nice is that the SensorThings API has a built-in support for MQTT. MQTT is an Internet of Things protocol, which allows you to enable some kind of push-based data delivery, so people can subscribe at such a sensor web server, SDA server, and then get live delivery of data as soon as new data are published. So let's first start with the data model of the SensorThings API, and you will see that there are some slight differences in the data models which we will have to deal with. So, for example, the sensor which has this taking a measurement is now called really a sensor, not a procedure in the more abstract O&M approach. Observation remains observation. The observed property remains an observed property. So the parameter which we are observing, the feature of interest, remains also the same. However, we get 2 new entities in here. On the one hand, the data stream. Data stream is basically aggregating multiple observations, and a thing. Thing could be an object to which a sensor is attached, which is then another IoT-specific concept which has been added here to the standard. So on the next slide, you see an overview of this. So this is basically taken from the SensorThings API specification. And to illustrate a bit what we are talking about here is, so we have as a central element the data stream. The data stream is new compared to the OGC SOS standard or ONM standard, and data stream basically aggregates multiple observations for a specific observed property, for a specific sensor, and for a specific thing. So that's a data stream. Each data stream comprises then the observations. Observations can be streamed on that data stream, and our thing, that could be, for example, a certain device which has an attached sensor that can also be placed at different locations, and we can express the historical locations here of our thing. But the important thing is, remember, in SDA we have so-called data streams as the core set for defining our data sets which contain the observations. So again, as a summary, perhaps that's a bit more for after the workshop, if you would like to reconsider certain things here. So we have the thing as the IoT device, the location of the thing, the historical locations of the thing, the data stream as our central concept, and then the basic things that you already have seen in the ONM data model. So the sensor, which has taken the measurement, the observed property, the parameter which we are observing, and the feature of interest, providing our geospatial reference to the observations. So, and now we will do some closer look at how to interact with such an SensorThings API instance. And what you see here is we do not have any more complex operation calls like get observation. We are moving to a REST-based or REST paradigm where we are accessing resources. So we have just URLs describing what we would like to access. Based on these resources, we can do some kind of filtering. We have the skip and top parameters, which allow us to do some kind of paging. So we can say, okay, I would like to skip the first 10 elements and please just provide the top 20 of the request. So this allows us to enable some kind of paging through a result set, which is returned by the SDA. That's important for client developers. With expand, we can get referenced entities in a certain resource also directly expanded, completely included in the element and the response. And we can also select certain properties which shall be returned. So we can say, okay, I would like to get a list of all my features, but I just want to have the names of the features. So you can compress the responses that you get. You can also have some information such as count. So how many entities are there to fulfill a request? You can order this. So ascending, descending by a certain parameter. Like I would like to get all features ordered by their name in ascending order. And you can do filtering. So you can do string matching. You can have some geospatial functions like bounding box filters. You can define dates, etc. So you have comparison operators for numbers. So filtering is quite powerful here, and it allows you to tell the server which specific entities it shall return. Very important, I mentioned that shortly, MQTT. MQTT is an Internet of Things protocol, which allows us to enable a push-based communication model. So we have so-called brokers. Let's do this here. We have so-called brokers which are receiving information from so-called publishers, and at the same time subscribers can subscribe at these brokers to get data as soon as new data has been published by the data producers. And the SensorThings API makes use of this protocol in two ways. One thing is that the SensorThings API can use MQTT to push information to subscribers, to clients. So if you, for example, are connecting to a SDA, you can tell the SDA, please push new observations via MQTT to me as soon as for a specific sensor new data is available. And then you can get push of the data via MQTT. And the other thing is you can also use MQTT to push data into your server. So for example, to connect MQTT-enabled IoT devices to directly get data into your SensorWeb server. Okay, so that was a quick introduction. And now I will try to illustrate a few of the SDA functionalities with a few example requests. And after that, we should also have some time left for open questions and discussion. So let's have a look at this. So what we have here is we have two servers prepared for this demonstration. One is an SDA instance provided by the Cost for Cloud project, which 52North is involved in, that is providing SensorThings API endpoint for citizen observatory data. Let me check. So I hope you can see my browser. And in here, you can basically see the different endpoints which we have, like the data streams. And here you have, for example, an observation data stream taken from a citizen scientist via mobile phone. The observations which are included in the streams can be then directly browsed here. And for example, here we have one person which has done such an observation. And this gives us then the opportunity to explore the data. And in this data stream, we have one observation. And here, for example, we have one observed property. Here are the observations. And then we have different parameters in here. For example, we can link to photos of certain plants observed. So this is a project about biodiversity monitoring. And here we have the citizen science observations, including references to the images taken by the citizen scientists as a result value. Further things are here. We can, further properties which are observed are, for example, the taxon name. So that's the name of the plant, the type of plant that has been observed. Phenophase, so the status of the plant, is it fully grown, is it just coming out of the earth, etc. So these are features which can be observed, and this is the first instance we are dealing with. The second example that we have prepared is a SensorThings API instance which we have set up for the AQSense project. This is a project which 52North is currently doing for the JRC, the Joint Research Center. And this project is dealing basically with low cost or lower cost air quality stations that shall complement the official networks of air quality information as an additional source of information. And JRC is working hard here in order to provide statistical approaches, how to fusion data from the official stations, from the local stations, in order to get a better impression about the overall air quality situation in Europe. And in this API, we have several data streams about data on the one hand from the official sources. So we are harvesting data from the environmental agencies of 3 member states which are participating to this project, and at the same time from the local stations deployed on behalf of JRC in 3 cities. And then we are providing here a platform to put this all together. And here we have the SDA SensorThings API instance for this. For example, we have here our data streams. Like this one here, this is a data stream from Oslo. Here we have a data stream containing PM10 particulate matter measurements from Aker Sykehus, which is the station name in the greater Oslo area. We get information about the data stream, so the unit of measurement, it's microgram per cubic meter. We have data from the 1st of May and until basically today. And then we can dive into this data stream by clicking or following this observations link. And then we can access all the measurements taken at this station you see here we have a result. So 14, you have seen the unit of measurement associated to the data stream, 14 microgram per cubic meter, measured on the 16th of August at 0 o'clock. And basically here we now have our data stream that allows us to access the data. We have up here our count. This tells us we have about 1,939 observations for this specific PM10 property at the station which we have selected. So that's the introduction of these endpoints. The endpoints are available on the web also after the workshop. If you would like to play around with them, you can do that. Yes, so let's perhaps have a closer look now into one of these APIs. One moment. So let's get back. So what we see, if we connect to such an STA instance, we get an overview of all the different entities. So this is some kind of landing page which are served by this STA. And the meaning of these different entities that you are seeing here is defined in this SensorThings API standard. So we have our data streams, we have the individual observations, we have the things, we have the locations, so these are the coordinates where sensors are measured, data is measured, the historical locations, the sensors, the observed properties, that could be, for example, interesting. Here we get an overview of all the parameters which are available here. So we have benzene, black carbon, carbon monoxide, nitrogen monoxide, NO2, O3. Here you see also the use of vocabularies as a very important thing. Here we have one entry, ozone, that's below here. Another data provider called O3, which is the same. If we would have vocabulary in place for this type of data, which is still really work in progress in many deployments, we would just have one entry referencing our vocabulary. Now, without vocabularies, we have to deal with different naming conventions by different data providers. And finally, the features of interest. This is also interesting. If you are developing a client application, you may call this endpoint initially to get an overview about all the different stations which are available. So you have directly here the identifier, like Antwerpen with a certain station ID. You have the coordinates. And with that, you could, for example, create an initial map showing you which of these stations are existing to build a nice map client. Okay, so that's the root. What you see there is basically really you get the URLs of all the entities offered by this SensorThings API instance. Next step could be, for example, that you look at the different things, so the different station or measurement devices in here. And if you have selected from the list of things, so we take now, we would like to get the download specific thing with a certain ID. So again here, so for example, we have specific things. This is our list of things. And if we would like to access a specific thing with a certain ID, we can put that ID into our URL, like ID 163, and then we can download this specific thing from all things that are available on our server. The same is with locations. And here, for example, I mentioned things may move around. It's quite seldom, but for example, with an air quality station, it may happen that due to some construction work, it has to move perhaps 20 meters along the street to a new location. And we can express these changes also by having these locations in there. And to get the current location of our thing, we just, as you can see here, need to query our thing and then append /locations to get the location of our specific thing. So let's try that in the browser to interact with the SDA. So here you see our URL, AQSense SDA things 163. And to get the location of this or all locations associated to this thing, we can, oops, that's an error. Perhaps some, I'm not sure which I did wrong, but then let's take the auto-generated link. /locations, and here you see the location associated to our thing RV for Akershus in Oslo. And here you have the coordinates of this thing. So let's continue. The historical location is then that we would like to see all locations where the thing has been in the past. Let's try this one also in the browser. Here I would expect that this does not change, but we will see exactly here. Our station Akershus was just at one location, and all the time it has been existing. So we just get one entry here if we call historic locations. What else do we have? Now we would like to get a bit more into the data measured by a certain station. And if we look now again at the browser here, let's go back again to our thing. So we have our Akershus station, and now we would like at the station which data streams are there. So we can click on this reference, and for this thing with a specific ID, we get now a list of all data streams available. We see we have 3 different data streams measured by the thing. One is dealing with PM10 data, one is dealing with NO2 data, and one is dealing with PM2.5 data. So here we can explore, we click on the station and get a list of all data available for this station. So it's quite nice to explore the content. And then if we have such a data stream, we can open it up with the specific identifier as a query parameter, and now we have our data stream. And let's see. The interesting thing now is that for each data stream, I have shown you before, we get the core properties, and via the observations link, we get directly to all measurement values available here at that location. Okay, that's it with that property. Back to the presentation. Now we are back. Yes. So same applies to the sensor. We have then information about our sensor, which we can also retrieve here. And this is something which I would also like to show you. So let's go back to our data stream description here. And here you see the link to the sensor which has taken the measurement. And the interesting thing here is now that you can also reference from the sensor further metadata about the sensor. Here we have some kind of break still in there because here we find a SensorML document encoded in XML. However, as SensorML is not yet specified as JSON, that's a workaround which is quite feasible at the moment. And here we get information then about detailed information about the sensor station or the sensor which has delivered our measurements. So even with SensorThings API, you can get all the metadata that you need for interpreting your sensor data. Okay, let's continue. The observed properties, I've already shown that we can explore the different observed properties which are available and can get the details here. The observations, I've shown them. So you get the result, the timestamp, and here you can see you have a phenomenon time, you have the result. That's pretty much taken from the O&M data model. Here you just have a JSON representation and not again an XML representation. So a bit more efficient, especially if you would like to build a client application. Feature of interest, we already had that. And then let's try again a bit with the filters that we have. So we can use filter parameters such as top, skip, and top for doing some paging. Let's do that in practice. So I will take the first one. let's insert it in here. So here we have in total 44 features of interest in our SDA, and with top 3, we would get the first 3 things. With skip, we would leave out the first 3 and get all the others which are available. And then if we combine both parameters, we can page through the whole collection. So we skip the first 3 and take then the top 3 of the rest, and that allows us then to build, for example, if you would like to build a client application where the user can navigate through a long list of stations, this can also be server-side supported with these skip and top parameters. Other could be to order the stations, so like order by name. We will also try this here. So here we have for to and verb. Let's see, I guess. Order by name. That's, I'm not sure. Yes, somehow it's ordering. So we have here, I'm skipping the first 3 ones, and then I'm ordering, and you see here name with C, E, H, and so on. So this is then the correct order, and we can even add the descending as an additional parameter. Oops. Jumping around a bit. So if I add descending here, order by descending, then this direction changes here. Here we have some values as now, these are listed first. And then one last thing, which is also quite nice, the features of interest. And we could also say we would like to get only selected parameters here. So in this case, we select only name, and then here we have those where no name has been defined, and then for all other stations, we get the corresponding just the name, which may also be interesting for some use cases where you would like to avoid unnecessary data transfer for processing the data in your client application. So you can really tell the server which specific elements shall be returned. So it makes it a bit easier if you are developing an application. So that's a very rough and quick entry into the world of SensorThings API. I hope that it at least got a certain feeling how this has changed beyond the SOS. And if you like, we will also be happy to tell you a bit more about this in the future. So just a quick last thing. So you have seen all these different specifications like the encodings, the SOS as an interface, the SensorThings API as an interface. And now for some of you, the big question will be, how do I get all this stuff into my existing IT infrastructure? Or how can I provide my data with this stuff? And here there are different ways. I will not go into too much detail here, but you can get this also for your reference later on, just to illustrate there are different ways how to get the data in there, and what we have also done in practice until now. So, for example, if you have an existing database which is already has already a certain structure, we can try to create some kind of object relational mapping between our sensor web components and your existing database through a framework such as Hibernate, and then we can just put this software on top of your existing database. If the changes are, or if there's no direct mapping possible, in some cases database view may be an option, also hybrid approaches, some views, some tables via mapping. There can be customized SOS database connectors. So if you have a database with your data in place, there are really different ways how to get that with as efficient as possible integrated into such a sensor web infrastructure. A more recent feature is the use of IoT protocols for data feeding. So, for example, if you have IoT devices, there are already nice boxes which enable existing IoT devices to talk MQTT as an Internet of Things protocol. We can connect to the data streams via MQTT from your devices to get that into the sensor web server. That's an option. You can use data feeders for loading the data into the infrastructure via the transactional operations. So, for example, you may have CSV files or some kind of very exotic database. Then you can use the data feeder, such an ETL tool like FME would be a nice option for this to enable such a data loading workflow. You can also have data feeding via SQL directly into the database, even also there with the help of additional tools such as FME. So different ways, or if you already are exposing some proprietary service which does not yet fully follow the OGC specification, there's also an option to deploy such a sensor web server on top of this as a proxy solution that encapsulates your existing endpoint and just translates between this existing endpoint and external, translating that to the standards of the OGC. So these are different options. And with that, I would like to close and see if there are any questions that you have. I guess this was quite a lot of information. It's always a challenge to put the introduction into this time slot, but I hope it was at least useful for you to get an entry into this topic. And of course, for all the 3 days of the conference, I will also be available during coffee breaks or separate sessions to talk with you if you have any more specific questions. Okay, with that, I would like to thank you for your attention.
Please use the Q&A tab for questions, and you're able to unmute yourself as well if you would like to speak up and ask a question, so you're invited to do so. To start up the discussion, question I would like to send is what can be expected over the next years? Simon, perhaps you can.
Yes, so over the next years, we have now seen this strong increase of the SensorThings API in popularity. I think that's a very important development which is already there. What's interesting regarding the standards world, some of you may have seen that the OGC is moving now towards a new paradigm, the so-called OGC API, which will define a consistent API for all the existing OGC standards to have a lightweight REST approach. And I see that there will also be a need to further move the SensorThings API towards this harmonized OGC API, because SensorThings was created a bit before this whole OGC API activity really took up some speed. And I expect for the next few years that there will be some further movement regarding harmonization towards the OGC API. So that's perhaps more the standardization part. And then technologically, I think Internet of Things protocols will be really important. So for example, I expect that data feeding via MQTT will be a very efficient thing for data publication, at least for getting raw data into such infrastructures. And also regarding data dissemination, I think that such push-based protocols like MQTT will help us to achieve also more scalability. So having timely delivery of the data and having efficient. So I think these protocols, real-time data delivery, that will be the other big part I would expect for the next years regarding the general technological development.
Well, thanks. Any further questions? Thanks again. Thanks for listening. We will publish the slides within the next hours, and we will prepare the video of this session, which will be available the next weeks or perhaps the next days. And we'll now have the coffee break, which is a session in itself, so where you can meet other attendees. Perhaps you've seen that you can use the community functions of Wova to get in contact with other attendees directly as well. to chat and to organize contacts and meetings. And after the coffee break, we will have 2 more tutorials this morning. One is about accessing environmental time series data for data analysis, which will take place here in this main conference room. And the other is about managing and using sensor data streams with ArcGIS, which will take place in the seminar room. Okay, so thanks again. Hope to meet you in the coffee break or in further sessions, and have a nice day.